Today we're going to solve some differential equations, and we're going to do it using separation of variables. And so kind of the key fact here that we're going to be using today is that if two expressions are equal, then their antiderivatives are equal. Okay, we knew when we did derivatives that if two things were equal, then their derivatives were equal. It's going to be true that their antiderivatives will be equal as well. So the first thing we want to do is find the general solution to the differential equation. Okay, remember when we were looking at the slope fields last time, the time before, whenever that was, we colored in solution curves. But we saw that there were a bunch of solution curves, a family of solution curves for every differential equation. And they were all separated by that plus c. And then the general solution was the solution that had the plus c, where c was allowed to roam over the real numbers. Okay, so what we're going to do is we're going to separate variables. And in this class, that is the only way we solve differential equations. Okay? If you're interested, you can look later on in that chapter in the textbook. They give you a couple of more techniques, but if the differential equation is not separable, then we will not be able to solve it, at least for the AP items. Okay, so what I'm going to do is I'm going to get the y and put it over there with the dy. So I'm multiplying both sides by y. So I've got y dy, and then I'm going to multiply both sides by dx as well, equals negative x dx. Okay. Now if these two things are equal, then their antiderivatives will be equal. Okay, well, I don't think we've taken any antiderivatives with respect to y, but if our expression is in terms of y, it's no different than taking an antiderivative of x with respect to x. Okay, an antiderivative for y with respect to y is going to be 1/2 y squared. Well, and then there's probably like a plus c also, right? And an antiderivative for negative x with respect to x is going to be negative 1/2 of x squared. Also plus c, but it'll be some other c. Okay, and in general, we're not going to add two plus c's. We're just going to say I could subtract this first c over here, and c2 minus c1 would be some constant, and I'm going to call that my plus c. So I've just got that. And now I'm going to solve for y. Okay, finding the general solution. This could be interpreted as a general solution as we have it, but overall, most of the time, they're going to ask you for a particular solution, which I'll get to in a second, and it's going to be y equals f of x. So we definitely want to be solving for y usually. Okay, so y squared, I'm going to double it, so that's negative x squared plus 2c. But again, we're not going to do algebra with plus c. Okay, so 2c is the same as just some other c. Then y, I'm going to take the square root of both sides. So I'm going to have the square root of negative x squared plus c. Or I might have the negative square root, depending on which point the solution curve passes through. Okay, we saw that sometimes the slope fields, it looked like there could be two different curves. Okay, well, it's going to be one or the other, depending on what your initial condition is. And so that's where that plus or minus comes in. The plus or minus will depend on the condition you were given. Okay, so why don't you all try this one? Solve this differential equation. This one's very similar to the last one. And you can check your working, it's fine. You're just using 1 plus c as time goes on. Okay, so the question was, why didn't I distribute the 2 to the plus c? And in a sense, I kind of did. Because over here, we've got this where c is really any real number you like, right? And so then really what I would have had is I'd have had y squared is 2x to the third plus 2c, where 2c is any real number. But if 2c is any real number, you could just call that some other real number like d or something. So we don't really need to be doing algebra or arithmetic with our plus c's, just as long as we have one. It's more important that we have one than that it track all of the changes to the constant over the course of solving for y. Okay, here we got another one. And this is one that you could kind of attack more than one way. I mean, you got to separate variables. That's not an option. It's not optional to separate variables. Okay, we're definitely going to want to rewrite this as dy dx equals square root of x divided by 3y. But you have the option of, you could either call this y dy equals square root of x divided by 3, or you could clear out the 3 as well. Okay, I'm kind of the opinion that if it was 2y, then yeah, I'm going to move it over because 2y has antiderivative regular y squared. So I don't know. It really doesn't matter. It's up to your judgment. Maybe I will. Maybe I will clear out the 3. Square root of x dx. And then I'm going to take the antiderivative of both sides. So antiderivative of 3y dy is equal to the antiderivative of square root x dx. Well, square root x is really just x to the 1/2 power. And an antiderivative for 3y is going to be 3/2 y squared. And this will be x to the 3/2. Then we're dividing by 3/2, which is like multiplying by 2/3, the plus c. And then I'm going to start looking at trying to solve for y on its own. So I'll have y squared equals, okay, if I want to get rid of the 3/2, I'm going to multiply by 2/3. So I'll have 4 over 9 x to the 3/2 plus 2/3 of c is still just some constant that's a real number. And it could really be anything. If you wanted it to be the same as it was before, you would need to change the earlier constant by making it, I believe, 3/2 of what it originally was. And then that means that y is going to be equal to plus or minus the square root of 4/9 x to the 3/2 plus c. But not all of these are going to have y in the denominator real nicely. Okay, these are just like some basic ones to get us going. Yes?
I'm going to take the antiderivative of the y side. Of y, I don't have c for the y side.
Okay, so the question was, why don't I have c on the y side? And you do. I mean, it's going to be a different constant, right? So it would be like, if I call that c1 and c2. And then when I go and subtract, to clear out this plus c2, I'd have minus c2. And if c1 and c2 are any real numbers, then their difference could also be any real number. So we just call that our general plus c. It's part of the reason why we just don't do much arithmetic or algebra with the plus c. And again, I promise you, the more you do this, the more comfortable you'll get with just kind of working with plus c, but not doing too much with it. Okay, here, now it's finally asking us to find a particular solution. So the particular solution was like, on the slope field, here's your starting point, color in the lines. Okay. We're going to do the same thing, except we're going to plug in x equals 1 and y equals 2 to find the value of c. So I'm going to clear out the y squared. So I'm going to have y squared dy equals 5x, multiply both sides by dx. I have that. Okay, I'm going to take the antiderivative of both sides. It's 1/3 y to the third is equal to 5/2 of x squared plus c. Okay. Since we're solving for y, and the reason that we know we have to solve for y is that it's saying find y equals f of x. Okay, so that means it needs to be an equation of the form y equals, and then some expression with a bunch of x's in it. Okay. Since I know that's where I'm headed anyway, that's why I keep the plus c on the side with the x's, because you're going to need to get it over there. Okay, I'm going to multiply both sides by 3, and I'll have y to the third is 15 halves of x squared plus c. Again, you could call it 3c if you really felt like it, but over time you're going to stop doing it. So might as well stop now. And then to solve for y is going to equal the third root of 15 halves of x squared plus c. And then now to get the value of c, I'm going to plug in y equals 2 and x equals 1. So 2 equals the third root. Well, it's going to need to be equal to the third root of 8. So that's 15 halves plus c. 15 halves is 7.5, so c would just need to be a half to get that up to be taking the cube root of 8. So that means that c equals 1/2, and y equals the third root of 15 halves x squared plus 1/2. Some t's. I had a question, why didn't I take plus or minus when I solved for y? And the answer is because I took the third root, and every number has a unique third root. Every number has 2 potential square roots, so that's why we do the plus minus. Or we actually would do that with any even root. So, but with odd roots, those roots are unique, so I don't need a plus minus. I think now would be a good time for y'all to try this on your own, find yourself a particular solution, and check your work against mine. We got to change y prime to dy dx so that we can separate variables. So why don't y'all stop once you get the general solution, because I forgot there's something more I need to say about this case. Okay, so that's my general solution. We got plus or minus the square root of 5/3, or 10 over 6, if that's how you feel, x squared plus c. And what's going to happen is I'm going to need to plug in 1, -2. But there's this plus minus thing. This is like always a tripping point for people on the separation of variables. Okay, the plus minus thing, what do I do? Well, -2 equals plus or minus the square root of 5/3 of 1, which is 5/3, plus c. Now, that's interesting. Is -2 equal to the positive square root or the negative square root of whatever this thing is going to be? It is the negative square root. So when you say positive or negative, it depends on the initial condition. So since y is -2 over here, we're going to be thinking, well, it's going to be just the negative square root. Okay, so and -2 is the negative square root of 4. So I need this to be 12/3, so c is going to be 7/3. So g of x is going to be the negative square root of 5/3 x squared plus 7/3.
positive, why would you just say it's just the positive?
Yeah, if y was positive, you would have chosen the positive square root, depending on just the initial condition they give you. So this is going to be one of those slope fields that has some sort of symmetry across something, to where if you choose a positive y, then it's going to do one thing, and if you choose a negative y, it's going to do something very similar, like mirror. We saw these on the slope fields, but I didn't even go into that because that would have just been more than needed at that point. All right, so here we've got another one. Except this one, okay, we're going to need to divide by y. So it's going to be 1 over y. Oh, I guess I'm going to replace that with dy dx. So 1 over y dy equals 1 over x squared dx. So, well, 1 over x squared isn't the easiest thing to take the antiderivative of. So I'm going to rewrite that as x to the negative 2. Okay. What's an antiderivative for 1 over y? Log of absolute value y, yes, equals negative x to the negative 1. Because if I took the derivative of that, I would get the negative 1 would come down, kill off the negative x to the negative 2. So yeah, positive x to the negative 2. Don't forget the plus c. And then, okay, so what I'm going to do is I'm going to take e to both sides power. So I'll have the absolute value of y is equal to e to the negative x to the negative 1 plus c. And this is equal to e to the negative x to the negative 1 times e to the c. It's one of our exponent properties. And e to the c is yet another constant. Okay? So we're going to just call that c. So we'll call that c e to the negative x to the negative 1. And that's absolute value of y. Now, if I'm going from absolute value of y to just y, how do I account for that on the other side? Do y'all remember from pre-cal? We did this just a little bit. Yes, yeah, you use a plus or minus. Because if the absolute value of y is equal to this thing, then y could either be this thing or it could be the opposite of this thing. So that's where we use the plus minus. C e to the negative x to the negative 1. All right.
Why can't you do the net log of x? I like of x squared.
Okay, so if you took the net, so question was, when I was anti-differentiating 1 over x squared, why doesn't natural log of 1 over x squared work? So let's look at natural log of 1 over x squared. That is always positive when x is non-zero. So the derivative of this is equal to 1 over x squared, which is going to be x squared, multiplied by the derivative of 1 over x squared. So that's going to be negative 2x to the negative 3. So that's equal to negative 2. I've got 3 powers in the denominator and 2 in the numerator, so that's negative 2 over x, which isn't the same as x to the negative 2. It's the chain rule specifically. But that's a common error, is to see something in the denominator and just want to take the log of the absolute value of it for the antiderivative. But the way to dissuade yourself from it is checking your antiderivative, especially now when we're new to taking antiderivatives. It's really good for us to check our hypothesis by just taking the derivative. Right, and now we're ready to plug in and find the value of c. All right, so y equals 3 when x equals negative 1. So equals plus or minus c e to the, well, that's going to be positive 1. Well, that's interesting. Well, first of all, it's plus or minus. It's not both plus and minus. Which one is it going to be? Is it going to be plus or is it going to be minus? Plus, because 3 is positive. Okay, so that means that 3 equals, if you want to solve for c, you're going to have to divide both sides by e. I feel like I copied this problem wrong, but it'll be all right. And then y is going to equal the positive of 3 over e multiplied by e to the negative x to the negative 1. And that's the particular solution. that was kind of sloppy, but got the job done. Okay, this one, dy dx is proportional to y. That's a very common differential equation. It's the type of differential equation you would see in like biology or economics or something. And it's actually kind of a simplistic model. There's a different model that we'll study in the second semester that really models almost everything that happens in the real world. But for now, this is, well, we're going to find out what type of model this is. So we're going to find the differential equation by separating variables. 1 over y dy equals 10 dx. I anti-differentiate both sides. Log absolute value y equals 10x plus c. Then I'm going to solve for y. I'm going to take e to both sides power. And that's c e to the 10x. Okay, I know I only did it once, but I'm making that jump. Okay, I know that e to the 10x plus c is e to the c times e to the 10x. E to the c is some other constant. You will grow more comfortable with that over time. All right, so that means that y equals plus or minus c e to the 10x. Okay, so it's an exponential model. Okay, and most likely it's going to be positive if it's an actual model of some sort of real-world phenomenon. Well, while I'm at it, I've got one more. Got a minute, so why don't I do the last one? Okay, this one is something that I could separate and solve. I could say 1 over y dy equals x to the third dx. And then I could solve it all the way down. But what if we had something like y prime equals x plus y? Anybody got any thoughts on that? Okay, but then you have negative y plus dy. And then you're going to try to... Okay, the thing is, this is not separable, and therefore we cannot solve this differential equation. Okay, so going back to the question I was talking about, I'm going to take the antiderivative of both sides, so that'll be log of absolute value of y equals 1/4 x to the 4th plus c, and then I'm just going to solve for y. Okay, so absolute value of y is equal to c e to the 1/4 x to the 4th. And then y is equal to plus or minus c e to the 1/4 x to the 4th. And that's a general solution, and so we're happy with that.